I'd like to start by asking the question of what it actually means to be human versus artificial. I mean, there are a lot of positive things, of course, but there's also a lot of negative. We get tired, we're fallible, we think we're right all the time, we think we're unbiased when we're definitely not. When we definitely are biased, and I could go on, but that'll put a downer on things. And one thing that we all know for sure is, think Brexit, think, the recent US election that's still ongoing. We don't agree. We very rarely agree on things, which is great. Competition is very healthy, and debate is very healthy. So we should definitely think of AI, artificial intelligence, as a great mediator, not the emotional one, but the logical one. And here's the key though, and this ties back into Rudy's talk previously. This is AI plus humans, and what we call HIL, or human in the loop. This is a software engineering term, HIL or SIL, which is software in the loop. So far as sight, or what we call perception in the AI field, any artificially intelligent system is vastly superior to humans with any kind of perception. It was years ago that we actually beat humans in threshold tests that have been improved year on year ever since. For sound or speech, or something called NLP, so natural language processing, or NLU, natural language understanding, as it's now evolved into, we're getting there. Definitely, there are so many nuances that AI is just rubbish at, simply because of that complexity. Taste and smell, there's actually not much, talking about our five senses, taste or smell, there's not much research out there. There's a little bit of cancer research because dogs can literally smell cancer, for example, looking into that. We've been researching the olfactory nerve system of dogs for hundreds of years, actually. But there's not much yet with AI. But touch or manipulation, so actuators and manipulation in robotics is a massively researched field. But the real power comes when you actually give humans the power of AI, of artificial intelligence, and that in itself encompasses a massive field with tons and tons of subsets. So forgive me when I use the term AI, it's actually a huge scientific field with many different subsets, machine learning, computer science, all within that. So because of that power, that's essentially why we invented it. This hasn't come out of thin air. This has been invented and is currently still being invented, and will probably continually be invented as the human race evolves. This is really if you think about going as far back as the beginning of civilization, the human era, the anthropomorphic era, is just a tiny little instance of the Earth, of the Earth's lifetime, or the universe's lifetime. And AI, artificial intelligence, is absolutely minute when you come to our technological progress. We're still in infancy. We talk about an artificially intelligent agent being on par with about a 3-year-old child, at its best. And if you take, for example, what we're doing right now, this wonderful world of webcams, AI already, and this is our products that we're already shipping, can give us these fancy backgrounds. It's AI that basically, as I move around like this, keeps tracking my head, and it means that I can block out my front room, which I'm stood in right now, etc. It can do really amazing things like reduce background noise, when kids are running through, and your dog's howling in the background, that kind of thing. But also what it's able to do now is it's literally creating I'm not sure Zoom has enabled this yet. I might be wrong, but there's a lot actually, being done in development right now. But what we're actually able to do is create a 3D representation of me, of you, and stream that versus massively sort of bandwidth choking real-time video. And you dramatically lower the actual data that you're pushing through your home broadband, your home internet connection, which lowers latency, improves the capability, but also at the same time you can take that representation and turn it into high res, even if you've got a completely rubbish camera attached to your laptop or your home setup. You can do a ton of little things, which is what I mean by those little value adds. And as I said, some of those capabilities have been implemented, some are about to be implemented, because it's an ongoing, evolving process. None of us knew that we would all be doing this, back in January. It's very, very rapid progress, but almost on an instantaneous basis that we have to come up with these solutions. However, I work for NVIDIA, and the company was built on gaming, since the late 90s. And what that means is we've been synthesizing life and creating realistic humans and realistic environments for a very long time. And there's now over 1 billion gamers that continuously demand extremely high quality, rendering Oscar-winning movies, for example, or robotic sims. And our latest GPUs, if you don't know what a graphics processing unit or a GPU is, that's them, the gaming cards, the GeForce brand, the latest brand at the bottom of that picture there. This is Ampere. So Ampere is the name of the actual silicon, the chip inside that does all of the work. And it's upped the performance again, but that was way back in March when we actually released it. There's been a lot happening since then. And as I said before, AI is a huge field, but we take data and with it we create a mathematical model. And here are some of the ones that are actually in use. If you take speech, as I said, NLP, natural language processing, the progress is literally insane. Just in 3 years, the parameters alone have grown from 65 million to over 175 billion different parameters. So GPT on that graph on the right there, it stands for generative pre-training, and it's a Google technique, Google research that requires a vast amount of compute. It would literally take over 15 years to train one of those models on a single Ampere GPU. However, if you cluster together a ton of GPUs, it can, you can do that same job in a mere hours, but it still does take hours because NLP is a massively complex job. And that's good because things like high fidelity sensors, such as South Africa's square kilometre array or large scale simulations of the COVID-19 genome take terabytes of data. So that's a million or 10 to the 12. A zettabyte, so that's the chart on the left there, is 10 to the 21 or 1,000 trillion. So that's what I mean by insane numbers. So today, this is your typical GPU accelerated data center or a supercomputer. The gold units that you can see there are our DGX servers. They have 8 GPUs in each, and the silver are the traditional CPUs. So this is what most people have got today. And this kind of setup, as it says there, with 50 DGXs, 600 CPUs, will set you back about $11 million. But it also takes about 630 kilowatts to actually run it all every single day. With Ampere, the new chip, this is all you need for the same performance. However, you've only got 5 units, so it only costs you $1 million, and it's only using 28 kilowatts of power, which means much, much lower carbon footprint. And yesterday, I think you were talking with AWS, Richard, about greener AI, and we mentioned this when I first joined the actual call. Our DGX superpods, which are a slightly different configuration to this, but on a similar kind of size, are now the world's most efficient. And this is actually our supercomputer that we call Selene in headquarters in California, in Santa Clara, and it's number 5 in the Green 500 list. However, no computer on the planet can compute everything. So we use something, well, we use lots of different techniques, but one of them is called partial differential equations, or PDEs. And they can explain concepts like fluid dynamics, or how water or air behaves, for example, across space and time. And computing these in Fourier space, so think signals or waves, you know, how we animate hair flying in the wind is all down to Fourier transforms. If we use Fourier space as opposed to just typical Euclidean, or height, width, depth that we know of, you can do this computation 1,000 times faster. And using neural networks, which are the basis of AI, it's what we're trying to make an artificial version of the networks in our own brain. If you use those as well, you can reduce error. And there's a recent paper out that actually just has proven on these Earth system models for climate, for example, that they've reduced the error by a further 30%. So what you can then do is, using a combination of our software here, these samples are of 1 kilometre resolution from the European Meteorological Centre, ECMWF, and you can produce a fully interactive simulation. I can only show you a video here, but you can actually go in, you can zoom, and you can really find out, and this is, accurate physical capability of a weather system in operation, and you can do all kinds of prediction, etc. One of the first things that I was actually involved with after I joined NVIDIA, which was 5.5 years ago now, I can't believe that, was setting up something called the Frontier Development Lab. So at its core, we basically use AI to solve existential threats to the planet. And here we're looking at a Ugandan farmer. And this summer, one of the teams spent 2 months developing an AI-based GPU-accelerated algorithm that can predict extreme rainfall within 5 days. So it gives her 5 days notice, which is time to harvest her crop before devastating floods. And they're actually developing a mobile app right now. This fantastic picture is a rendering, and it's again part of the one of the summer's challenges called Moon for Good with NASA, where we're basically helping to find water and therefore suitable landing sites for the landings that are going to start taking place back on the moon's surface. This is the Faustini crater near the moon's south pole, which is permanently dark. It's permanently in shadow. It's called a PSR, permanently shadowed region. Combining physics with something called real-time ray tracing, where we're literally using the GPUs to follow the rays of light themselves and get that, really high-res photorealistic capability that gamers demand, for realism. We're basically able to illuminate these PSRs, and so that helps in the search, but also, as I said, for landing sites. But we're not limited to following just rays of light. You could essentially use this same technique for any, characteristic within the electromagnetic spectrum. So, we're just scratching the surface on that, literally. There's a ton of people that were involved in this work, again, this summer, which predicts lightning, which essentially starts most wildfires. The paper will actually feature at the world's #1 AI conference, NeurIPS, next month, as well as COSPAR, which is the space research conference. And what they do is they essentially take the GOES weather satellite, and they take the data from that to provide 15-minute warnings with an incredible 50% reduction in false alarms. And false alarms are, we know just from car alarms, they're not a good feature. Essentially, to address climate change, our first priority is to stop deforestation. And what you can do is you can use Earth observation techniques, or EO techniques. So that's satellite data of the entire globe. And with that, you can actually rapidly identify areas just with a computer vision solution. And these are areas that have changed radically over a period of days or weeks. So we can literally see all over the globe now. And I'm currently working with the UN and the European Space Agency on such a project, which is, really cool. This is a forest through the eyes of an autonomous drone using LiDAR and cameras. So this is the same way that a self-driving car sees the world. The actual word autonomy means simply that the drone doesn't need a human to fly it, only to top up its battery every 5 or 6 hours. And this is actually work with UPenn, so University of Pennsylvania's GRASP Robotics Lab. And they've actually just, one of their researchers, a guy that I work with, Stephen Chen, has spun off a company called TreeSwift. And they're literally selling this research now. Obviously, the timber industry, which is trillions of dollars, is very interested in it for monitoring, but also for disaster response, for wildfire management, for example, because these drones are able to be put into an area and it maps in high res entire forests in extremely accurate resolution. In under an hour, for example, depending on obviously the size of the forest. And it really is, climate change really is this black and white. As we all know, melting ice means blacker surfaces, which absorb more sunlight. And as the ice melts, the permafrost thaws, that releases methane, 20 times worse than CO2. We know this, but we also now know that this process cannot be stopped. There was a recent Nature paper. I don't know if people have missed that or not, and that's no matter what we do. So we simply have to adapt. And something else that I'm working with the UN on is putting together this digital ecosystem, because 2/3 of the environmental sustainable development goals, so the SDG indicators, cannot yet be measured due to lack of data, because we haven't yet harnessed AI with Earth observation, with satellite data. So putting this digital ecosystem into place for everybody to use is really critical to assess and predict risks, to increase transparency and accountability in management of resources. But just obtaining that information, or having a website that shows areas of deforestation, literally nudges population level behavior and makes folks aware of the situation that's happening right now. But luckily, we are a technically advanced civilization. This is San Francisco, and it was taken by a unit called HEIST in 2019. So OSK, or Orbital Sidekick, are a partner of ours, and they deployed HEIST back in 2018. And it uses our embedded GPUs that are about the size of a credit card to enable something called hyperspectral imaging. So this is images on multiple spectral frequencies. And here's HEIST when it was living just outside the International Space Station on one of its external platforms for over a year. Sitting here, you can actually just see the unit far right under the white canopy. Their business model is literally monitoring for farmers, for defence, for shipping companies following shipping lines, etc. This is the latest version of the embedded GPU. That's the development kit that you can get for testing and prototyping on the left, and that's the actual production module, which is depending on your screen size, it's 70 by 45 or almost that size. Even software is getting easier and easier. With hardware is one thing, but it means nothing without the software. But a key component of NVIDIA's entire ecosystem is something that we call NGC, or the NVIDIA GPU Catalog. And it's essentially a hub of free, completely, utterly free, optimized software in easy to find and easy to use collections. There's over 100 different pre-trained models. So it's basically designed for immediate software engineering, immediate deployment, and every single one of them is validated for performance, quality and security. But the really interesting thing is creating an accurate neural network or an accurate AI system requires a massive amount of fine tuning. or training. It's a very, very complex process, but we've done most of the hard work for you, because you can just pull down a pre-trained network to do some fairly, standard AI value add, to create those small value adds. But on the other side, the beauty of AI, of these neural networks, is that you can use them to actually train themselves. So we're now capable of having an AI system make itself the most optimal neural network that it is, if that makes sense. We're going into. And this is actually 2-year-old work, the paper reference there on the slide, from Facebook and Stanford. And there's been a ton more happening in the neural architecture search space. But from my point of view, the most exciting part of my day job is what we do in the world of virtual reality or extended reality. So NVIDIA spent decades working on what we call the metaverse or virtual worlds. Obviously, starting from scenes for games, scenes for training, virtual cars to drive safely through virtual cities with virtual people, etc. But how do you put physical accuracy into a virtual world? Is that video working? Can you see it? So basically, what you do is you simply pick an object in a scene and you apply physics to it. It's literally as simple as that, because we already have had something called physics, which is a physics engine, for over 20 years, and it's in constant development. It's also an integral part of what we call now Omniverse, which, coupled with all the goodness from the gaming world and the movie world, so Disney has Pixar, and Pixar has universal scene description, and this allows it to be easily implemented, and we can literally create anything in that virtual world. That's just a still image, for example, but virtual robots, again, this is just a still image, but virtual robots, including cars, can be fully developed and fully tested before they go into the physical world. And we have research papers that have been published, accredited papers, that actually prove that combining its simulation with reality improves the overall results. Because, of course, we can come up with all kinds of different corner cases and, literally pluck out of thin air, or, the crazy corner cases that we may never think of. As you can see here, we've got hundreds of virtual robots that are being trained in a virtual world with something called reinforcement learning, which is a type of extreme trial and error learning. To grasp a drawer and open it seems fairly trivial, but note the accuracy of the blocks moving inside the drawer. This is a fully physically correct and accurate simulation environment. And the platform Isaac is free to everyone to use. Isaac Sim, Isaac Gym is the reinforcement side. The whole thing runs on GPU, and it's training 2 separate neural networks to perform locomotion and obstacle avoidance. And once the training's complete, you simply take the code or take the weights and put it into a real robot. So that real robot will then perform accurately and safely. And this is another virtual robot, the flat yellow thing, which is actually called an STR. And it's been trained completely in the Isaac platform, and it's fully used now by BMW in their German production facilities. So what they do is, using these test facilities, they can fully get compliance, all ISO standards achieved, before they actually put the real object into their real production facility. The AI compute on board is our embedded GPUs, our Jetson and Xavier. And, we can digitally twin anything, literally, that you can think of. So I'll close up now by saying that you and I we're currently trapped on Earth by gravity, but stood on the moon, which others will be doing again very soon, in just a couple of years, 2 or 3, maybe 2023, 24. This would be your view. So in the foreground here, you can see the far side of the moon. This is actually the high-rise shot from quite a few years ago, actually now. And it's clearly showing the continent of Africa, where civilization began. So closing thought would be that with humans plus AI, absolutely anything is possible. And we should really remember that. I've only had time to give you just a few highlights here. So if you do want a deeper dive in the hows and the whys, we've got a full training curriculum that spans from fundamentals to industry-specific applications, teaching you literally hands-on how to build and deploy neural networks in a variety of different tasks using our software and actually using our GPUs in the cloud. And in most cases, we actually pay for the GPU on your behalf. So that's it. Thanks for listening, and happy to answer any questions.